We continue our study of parametric equations by studying projectile motion. Projectile motion is a form of motion where an object moves in a parabolic path. The path that the object follows is called a trajectory. In projectile motion, the horizontal velocity remains constant and the vertical velocity increases due to gravity. So how can we have a vertical velocity and a horizontal velocity? It's because we go back to vectors. Velocity is a vector, and we're going to break it down into its two components. If the angle of trajectory is theta, then this component is v naught cosine theta, where v naught is the initial speed of the object, and theta is the angle from the horizontal at which the projectile is launched. So this part is the portion of the velocity in the horizontal direction, where this is the component of the velocity in the vertical direction. Gravity does not affect the horizontal component of the velocity, it only affects the vertical component. So that's why we need to look at this as two separate parts, the vertical part and the horizontal part. We're also going to use the letter h as the initial height above the ground. Sometimes we launch things from the ground, like kicking a football or a soccer ball, whereas we might be launching something like that, like a bow and arrow, pulling that back, or hitting a ball in midair with a baseball bat, launching something from a cannon, all types of situations. We have our parametric equations. Remember, parametric equations introduces another variable, and in this case, we're going to look at the variable t for time. The horizontal component of the path of the projectile is this. You may remember from a long time ago, a previous class, that perhaps speed equals distance divided by time. And so if you solve for distance by putting that t on the other side, you would get speed times time equals distance. So x is going to be your distance in the x direction. This is your velocity or speed in the x direction. And then we have t as time. Vertical component, much more complicated because of gravity. We have this. We have negative 1/2 gt squared plus v naught sine theta, and remember that's the vertical component of your velocity, times time, plus any initial height you may have. So we have this part due to gravity, this is the vertical component of your velocity, and then any initial height. Notice all vertical parts of the path of the projectile. Since the vertical component of equation is a parabola, notice we have t squared and t, the vertex of that parabola will give us when the projectile reaches its maximum height and what that maximum height is. I'd like to develop that equation. So if we rewrite this in terms of something a little bit easier, like a quadratic equation, saying a t squared plus bt plus c. I'm going to use the t's since that's our variable. How could we put that in a format where we could find the vertex? Well, remember this? We had y minus k times 4a equals x minus h squared. And so that part, h and k, were the vertex of that parabola. We're going to do the same thing, except instead of x here, we'll have t. So how do we get that into that format? We're going to complete the square. And yes, it's going to be a little bit ugly, but hold on. All right, so we have this. We're going to subtract c from both sides. And remember, in order to complete the square, that coefficient has to be 1. So I'm going to factor out that a. In order to factor it out here when it's not there, I'm just going to divide by it. Convince yourself, if I multiply those together, I would just get b times t. Now in order to complete the square, I take half of that, square it, and add it to both sides. Now the right-hand side is the part I'm kind of focused on. If I rewrite that in factored form, I get that. And yes, you could put that together, but hold on. This portion matches that part, which gives me the t component of the vertex, which means it tells me when the projectile would reach its maximum height. So we have this, that would be the vertex, and I'm looking for that x coordinate, or in this case, the t coordinate. So if I solve for t, t would equal to negative b over 2a. That's when the projectile reaches its maximum height. Now you could actually put this together and memorize another formula of what that maximum height is, but I'm going to approach it a little bit differently. So hold on to that. I think that's a pretty easy formula to memorize. If you think about it, it's the first part of the quadratic formula, and of course the quadratic formula comes from completing the square on a quadratic. So we have all of these fun-filled equations and formulas. How are we going to use it? Well, first of all, let's look at something where the ball goes straight up and down. So Herman throws a ball straight up with an initial speed of 40 feet per second. So your initial speed, that's that v naught, v with a subscript of 0, that's 40 feet per second. From a height of 5 feet, so remember that initial height. So we've got, here's Herman tossing a ball up, and it comes straight back down and hits the ground. So what is theta? Is there an angle of elevation? What's straight up? 90 degrees. Do we know anything else? I don't think so. So part A, find the parametric equations that model the motion of the ball as a function of time. Remember, we have two of those. We have x equals v naught cosine theta times t, that's the horizontal, and then we have this one. Now g is 32 feet per second squared. That's a constant. So those are our two equations. What do we know? Well, we know v naught is 40, so we could put that there. We also know that theta is 90 degrees, so we could put that there. And we also know h, so we can put that there. First of all, look at your picture. Do you have a horizontal part? If you throw a ball straight up into the air and comes straight back down, is it going to go anywhere side to side? No, but let's just look at that. What happens? X equals 40 times the cosine of 90 degrees times t. Well, what is the cosine of 90 degrees? That's 0. There is no horizontal component. Let's look over here. Let's simplify this a little bit. We have negative 16t squared plus 40 times the sine of 90 degrees plus h. Now what's the sine of 90 degrees? It's 1. Oop, and I left out my t right there. And h is 5. So part A is find the parametric equations that model the motion of the ball as a function of time. I've got that. Now part B, how long is the ball in the air? Not the maximum height, not when it reaches the maximum, but how long did it go up and down? How can you figure that out? You can set y equal to 0 and solve for t, because y is 0 when it hits the ground. T will tell us how long it traveled. So let's do that. So I'd have 0 equals negative 16t squared plus 40t plus 5. That's a quadratic. It's not going to factor. You're going to need to use the quadratic formula. You need to get out a calculator. So this time we're going to be solving for t equals negative b plus or minus the square root b squared minus 4ac all over 2a. Might want to check my arithmetic here. I think it's right. So as we plug that into the calculator, your calculator doesn't have a plus or minus sign, so you need to do it 2 times, one with it plus and then one with it minus, being very careful, and you're going to get 2 answers. You're going to get t equals negative 0.12 approximately, kind of depends on how you round it, and t to be 2.62. These are in seconds, right? So can you have a negative time? No. So the question is, how long is the ball in the air? 2.62 seconds. What does part C ask? It asks, when is the ball at its maximum height? When is at the maximum height? Well, we had a formula that t equals negative b over 2a. We're looking at that. So we have our a, our b, and our c, just like we did for the quadratic formula. It's the same a, b's, and c's. So b is 40, a is negative 16. Plug that in. Going to have negative 40 over 2 times negative 16. You have a negative over a negative. That's good. 1.25 seconds. That's when it reaches the maximum height. So what does that tell us? Something you cannot do. You cannot just take half of that number. And that is because we didn't get a full parabola. Remember, it started here and came back down, so we didn't get that part. So you can't just take half of your total time. And part D asks, what is the maximum height of the ball? Again, you could memorize a formula, but you're going to have so many to memorize. I think it's better to really understand. What is the maximum height? Well, that means what is y when t equals 1.25 seconds? Remember, it took that long to reach the maximum height, so let's just solve for y. And again, remember, we're going to use our equation that we developed, and we're going to plug in t to be 1.25. Punch that carefully into your calculator, and you should get 30, and again, that's 30 feet. Seems like a reasonable answer. So we have found the parametric equations, we found how long the ball is in the air, how long it took to reach the maximum height, and what that maximum height was.